wabarakatuh. Good afternoon to all the participants. I am Vika Marcelina from Physics of Magnetism and Photonics Research Division, Faculty of Mathematics and Natural Sciences, Bandung Institute of Technology, Indonesia. In this section, I would like to present our recent study about reduced graphene oxide, titanium dioxide composite as counter electrode in platinum-free dye-sensitive solar cell. Dye-sensitive solar cell, as we know, is built by photoanode, electrolyte, and counter-electrode. There are three important roles counter-electrode in dye-sensitive solar cell. First, as the catalyst that boosts the completion process, and then collect the electron from external circuit, and as the mirror which reflects and absorbs light from the cell back to the cell. Platinum is commonly used as counter-electrode, has some advantages like high conductivity, chemically stable, and so on, but it has high cost and limited availability. So we have to find the alternative for platinum replacement material. One of alternative material for counter-electrode is graphene. Pristine graphene is one of carbon-electrode that has some outstanding characteristics like high electromobility and high surface area. For large application, we can use graphene-like material, which is reduced graphene oxide, or RGO. Another nanomaterial is titanium dioxide nanoparticle. Titanium dioxide is semiconductor material that has high specific surface area, available in large quantity, non-toxic, and good addition to the substrate. With those advantages of RGO and titanium dioxide, we can combine this material to be RGO titanium dioxide nanocomposite for counter-electrode in dye-sensitive solar cell. It can increase specific surface area, improve catalytic activity, and then enhance dye-sensitive solar cell performance. For making dye-sensitive solar cell based RGO titanium dioxide nanocomposite counter-electrode, first we prepare clean FTO substrate, then we prepare titanium dioxide mesosphere that immersed in Z907 dye as photoanode. Then we made RGO titanium dioxide composite with different ratio in weight, which is deposited using spin coating and replasting method. The last, we assembly all the electrodes using soldering as special and mosellite as electrolyte, and we characterize the cell using Raman and IV measurement. With Raman spectroscopy, we can investigate features for carbon such as G-band for sp2 hybridized carbon atom, D-band for defect in carbon ring, and 2D band for graphene characteristic. From IV measurement, we can obtain the fill factor and efficiency of the cell, then we compare using other different electrodes. Show Raman spectra of RGO and RGO titanium dioxide composite. In Raman spectrum, we found that G-band has higher intensity than D-band, with the ratio of D-band and G-band is about 0.85. It is indicated that RGO and RGO titanium dioxide composite may possess low defect density and result in good quality of RGO. However, for counter-electrode application, defect in graphene or RGO play role catalytic activity for reducing iodide triiodide ion in dye regeneration. The JV characteristics of the cell are shown in Figure 9. It was found that cell A that used platinum as counter-electrode showed photocurrent density value of 7.4 mA per centimeter square, fill factor of 49.67%, and power conversion efficiency of 2.5%. However, when the counter-electrode was replaced with FTO only, the diode characteristic was not observed. Meanwhile, when the counter-electrode is RGO titanium dioxide composite in film with spin coating deposition, its photovoltaic characteristic has lower performance than cell A, and showing a shift. It may be due to the species electrode contact with FTO substrate and possibilities for potential loss. Compare with the counter electrode using LGO titanium dioxide composite in film with drop casting deposition, it shows that JV curve with quasi-square shape. It's predicted that cell D has lower recombination loss than cell C, since the film, which is deposited on the FTO substrate, is thicker and inhibits species electrolyte reaching the FTO substrate. To see the effect amount of LGO, we compare with different ratio of LGO and titanium dioxide of 2 to 5 in weight. The cell with the LGO, TiO2 nanocomposite in film using drop casting deposition, showing slightly higher current density value than cell C and D. Cell F, using spin coating deposition, possesses higher current density value than cell E. This indicates that lower amount of LGO and LGO titanium dioxide, it may improve catalytic properties of counter electrode, since lower resistance of LGO in ratio 2 to 5 than 4 to 5. With lower thickness, it may provide sufficient area for reduction iodide 3 iodide ion and affect higher JSC value than cell E. However, the current density and efficiency of the cell are still lower than using platinum counter electrode. Last, with the cell using LGO titanium dioxide composite in ratio 2.5 with optimum thickness, we obtain its photovoltaic characteristic emerge with almost similar cell performance as cell E. However, this measurement result shows that this LGO titanium dioxide composite electrode has catalytic activity for redox couple of iodide 3 iodide electrolyte as effective as the platinum counter electrode. In graphene catalytic properties, the graphene H plane has good catalytic side and the basal plane has poor catalytic side. So when we deposit flat graphene plates, the effective catalytic side area is low. This is different when graphene plate wrapping titanium dioxide nanoparticle. It will result in broad graphene plate with high graphene H exposure with high catalytic area. So it will have good performance for counter electrode. We can conclude that we have successfully made LGO titanium dioxide composite film for counter electrode in dye-sensitive oxide by using a single way. From the present result, LGO titanium dioxide composite can be also a prospective candidate for the replacement of platinum-based counter electrode. Efficient catalytic activity at counter electrode is attributed from effective exposure of graphene H site in this reduced graphene oxide titanium dioxide composite and adequate protection of FTO from direct contact with electrolyte. Although titanium dioxide is commonly considered containing many trap states and can thus increase electron recombination loss, such effects seem negligible in this reduced graphene oxide titanium dioxide counter electrode. Authors would like to acknowledge the support from Osaka Gas Foundation ITB 2021, and I acknowledge the support from LPDP Scholarship for the Study Master Program. Thank you for visiting our poster.